So last time, you remember we looked at, we wanted to take the biggest collection of sets where every two sets had non-empty intersection, right? This time we're going to look at something else related to intersection, but it's going to be a little bit of a different condition. So basically this time we want to find sets, a bunch of sets where all the intersections are equal to the same set. So let me give you a definition. A sunflower that is what people actually call it, with p petals is a collection, let's say, I don't know, F, let's call the sets F1 up to Fp. So it's a collection of p sets such that there exists a set C such that, it's kind of a double such that, Fi intersect Fj is equal to C for all I not equal to j. Between 1 and p, of course. Right. And we call C the core of the sunflower. Okay. The reason we call this a sunflower becomes clear if you try to draw a picture, right? Kind of the way this looks is something like this. You've got like a bunch of sets, F1, F2, F3 up to Fp, and this is like the core, you know. And yeah, every two sets in the collection intersect in the same place. They intersect on the core. One thing to notice here that actually is kind of important is that I never said that the core had to be non-empty, right? The core is just a set, right? It could be the empty set. So this is a sunflower here, but also if I was to take a bunch of disjoint sets, so this is a sunflower with an empty core. So it's like you pulled off all the petals and yeah, they're just laying there. That's considered a sunflower as well. Yep.
Is it a condition that all the sets need to have the same number of elements?
In this definition, I'm not saying that, but actually, in the thing we're going to prove, they're all going to have the same number of elements. So, yeah, you can just think of these sets as having the same number of elements. Technically, they don't really have to, but that's our application will have that property. Yeah, our well, not application, but the thing we're going to prove. Any questions about this? Okay, so what are we going to prove? Well, so kind of a natural thing to ask. Suppose I take a lot of sets of size k, let's say, so all the same size. At some point, if I take enough of them, do I always have to be able to find a sunflower? Right? I mean, of course, if you take a bunch of disjoint sets, you're going to find a sunflower. But now take lots and lots of sets of size k. Are you guaranteed at some point, if you take too many sets, that you're going to have a sunflower with p petals somewhere in that collection? And that's what we're going to prove. So, well, so this is the known as the Erdős-Rado. Two people from last time. We had Erdős-Rado last time. Now we've got Erdős and Rado. Sunflower lemma, which I'm confusingly calling a theorem. So if I take, so actually in this case, last time for Erdős-Rado, we were taking subsets of the numbers 1 up to n. In this case, I don't actually really care what the ground set is. Like we can actually take these in an infinite set. So I'm going to take a collection in the natural numbers choose k. If we remember from last time, these are just sets of size k, which are subsets of the naturals, right? So if this thing is really big, sorry, this should not be greater than or equal to, strictly greater than k factorial p minus 1 to the k. Then F contains a sunflower with p petals. Okay. So if the collection is big enough, you're always going to be able to find, if it's super large, you can find a sunflower as big as you want by, making this bigger. Any questions about that? Clear? Yeah. That's right. Actually, maybe that's confusing that here I called F the actual sunflower, but here what I mean is that there's a way to choose P things in this collection that form a sunflower. Totally, yeah. Any other questions? So, this is motivated by lots of applications. Apparently, there's a lot of applications in computer science, like things like problems related to circuit complexity and parameterized algorithms. That's not really part of this course, so I'm not going to get deep into that. But yeah, sunflowers do have a lot of applications. Let's just focus on proving this, though. Well, OK, so we're going to do induction on K. So for any fixed, just fix the P, and then we're going to go by induction on K. Base case. Yeah, I don't think there's any sense in thinking of k equals 0. Let's think of k as 1. So maybe here k is at least 1. So does anyone see why this works? So this is going to say k factorial is 1, right? So this is just saying that I've got sets of size 1, right? And I've got greater than p minus 1 of them. So I've got at least p sets of size 1. You see why that makes a sunflower? Yeah, it's just one of those kind of sad, ripped apart sunflowers, right? So I've got, so F has, at least p sets of size 1. And yeah, that makes a sunflower. So sunflower with empty core. Okay, that's kind of trivial. Let's do the interesting part. Okay, so here's the idea. Let's first just look in our collection and find as many disjoint sets as we can. Obviously, if we can find p of them, we've already won, right? We've got our sunflower. So you're not going to find p of them. So in other words, so let's say A, what's notation do I have? Yeah. So take a subcollection A1 up to AT. Such that, A is a subset of F. All the sets, in A are pairwise disjoint. And T is as large as possible. Well, so this observation we just had is that if T is at least P, then we win. Right? Because then A is a sunflower with P petals. Okay, so we're going to assume T is at most P minus 1, right? Okay, so let's look at so we've got all of these disjoint sets, right? We take as many disjoint sets as possible. And whatever. Well, now here's the thing. Suppose I take a set in F that's not in A. By kind of the maximality here, that set's not going to look like this, right? It's not going to be disjoint from all the sets in A. It's going to touch this somewhere. And so essentially what we're going to do is kind of go over all the different points in the union here and look at all the sets in F that touch that point and kind of treat that as a kind of subcollection and apply induction on it. Let me tell you a bit more formally what I mean. So let's say X is the union of all these sets. And for each x, little x, and big X, let F sub x be the set of all sets in, let's say, B in F, such that X is an element of B. Well, Well, we can say this, right? F, like everything in F is going to be in one of these sets Fx, because if there was a set in F that wasn't in Fx for any x, that would just mean it's disjoint, right? From all the sets in A. Okay, so, and these things, of course, they may overlap each other. We don't know anything about it. But certainly we can say, as an upper bound, we have this. But remember, we had some bound on F from the beginning, right? It's at least k factorial. So I apologize, this is a little bit tiny here. But the size of F is strictly greater than k factorial p minus 1 to the k, right? Now we can do a little bit of pigeonhole. So then we can say that there's some x in x such that this fx thing has size at least, or strictly greater than, k factorial p minus 1 to the k over the size of x. Right? Because I'm summing up size of x many things that add up to more than k factorial p minus 1 to the k. So one of them must be bigger than kind of the average size. So this is by, PHP, pigeonhole principle, right? Questions at this point? Okay. Hard to judge if this is too fast or too slow or what, but right. So, well, okay. How big is the size of x? Well, it's not that big, right? Because t is at most p minus 1, right? And all of these sets have size exactly k. So that you've got k. All of, the k, x is a union of sets of size k, of which there's t of them, and t is at most p minus 1. So I guess kind of back myself into a corner on that board. But what I'm trying to say is that the size of x is at most, or it's equal to t times k, which is at most p minus 1 k. So therefore, there exists x such that fx is strictly greater than k factorial p minus 1 to the k over size of x, which is at most this. So plug that in. Okay, and lo and behold, this gives you kind of the right thing for applying induction, right? This is like the same as the bound on F, except it has a k minus 1 instead of a k. However, I mean, we can't really apply this directly to fx, right? Because fx is a bunch of sets of size k. Like, if we have a collection of sets of size k minus 1, which is this big, we can apply induction. But these sets have size k, right? Anyone see what we're going to do? Yeah, x is kind of redundant, right? X is in all of these sets, right? Take it out. Find your sunflower. put it back in. It's in all the sets. So it just goes into the core, right? So remember, fx, yeah, x is in all of the sets in fx. So yeah, it is completely redundant. Take it out, apply induction, put it back in, and then you're done. So, so in other words, like if I take, so define, so the collection, if I call it fx prime, so this is b minus x for b in fx. So it's, it's an n choose k minus 1 and has size strictly greater than k minus 1 factorial, p minus 1 to the k minus 1, because it's the same size as fx. You maybe have to think a little bit that this doesn't cause two sets to become the same set, this operation. Generally, if I just pluck things out of two sets, they could become the same set. But because all the sets in fx are distinct, and they all contain x, like taking out x from both of them can't make them into the same set, right? So it has a sunflower with p petals, and then adding x to all sets in the sunflower gives us what we wanted. So it gives us 1 in fx and therefore in f. So now x is in the core. Okay. Does that make sense? This is kind of a cheap kind of a little bit of a basic argument, right? Just pigeonhole. Well, I mean, maybe it's smart to think of this biggest disjoint, collection of disjoint sets. Then you just do pigeonhole, and it's pretty quick, right? Last time in this Erdős-Corrado theorem, remember the theorem we proved was best possible. It was like we proved an upper bound on the size of an intersecting family, and that was tight, right? You might then ask, what about this sunflower lemma or theorem? Is that tight? Like, if you have or could you prove maybe a better bound? And this is, so it's, I mean, that's a major open problem. So, well, it's not an open problem anymore. It's known that it's not tight. So the bound, like k factorial p minus 1 to the k is not tight. In particular, people are kind of generally skeptical about this kind of dependence on like k factorial here. So k factorial is kind of like, if you know Stirling's approximation, k factorial is something like, okay, I'll write the proper form. It's like root 2 pi k, k over e. So all of this that I'm saying now is kind of an aside. But basically, it's kind of like k to the k, or k over e to the k. So in some sense, this is kind of like k to the k, p to the k. If you think of k factorial as being something like that, right? And Erdős and Rado conjectured that you don't need this k to the k, that really there should be no dependence on k in the base of the exponent. So it should be something like some function of p to the power k. Maybe replace the p with some other function of p, and that's all you should need. But that's not that's a conjecture. Okay. All of these remarks are not really in the core material of the course, just kind of an interesting thing. Questions? By the way, I think the best known bound, I think somebody has been able to prove something, a bound like this or something. So instead of having like k to the k, it's kind of like a log k to the k. But I think that's the best anyone knows. Okay. Okay, so with the two things that we've proved, I guess it's kind of hard to get a sense of where this course is going, right? So I think in a lot of math courses, I think the focus tends to be, you develop methods. For each method you develop, you see what can I solve with that method. Calculus, you figure out how to do derivatives, and then you start solving problems like farmers with fences, and see what you can solve with derivatives. You learn how to do an integral. You integrate stuff, find areas and volumes, and blah blah blah. Sort of the focus of this course is more going to be on, let's start with a problem. How do we solve it? The method's going to come from that. Often different problems from different areas are going to use the same method, or we're going to have different sort of methods coming up. So let me kind of say something about sort of some methods we'll encounter, or I don't know if method is really a word, kind of, well, some kind of ideas. So basically, this is going to be a problem kind of focused course. And for each problem, we're going to, that's kind of how math works in the real world, right? You try to solve a problem. You don't know how you're going to do it. And then we figure out how to do it. So like we've already seen in the Erdős-Corrado theorem, for example, we had double counting. In this Erdős-Corrado theorem. Today, what we saw is something like, pigeonhole principle. These ideas are pretty ubiquitous. They're going to come back. Induction. One thing that's going to come up over and over and over, and that's why I'm going to spend the next 20 minutes on it, on basics of it, is convexity. And that's going to come up a lot during the course. I don't know, I wrote down some other things here. I guess linear algebra is going to come up. Sorry. And fancy sounding things like entropy, topology, and probably other kind of methods. None of this should scare you, though, if you don't know about topology or something. It doesn't really matter. We're going to build up everything that we need for it. So let's talk about this convexity thing. So I think this is, in my notes, this is like appendix, I think, C. Okay. So basically, you're going to have to get really familiar with things like Holder's inequality and things like that. Well, let's start at the beginning. So what is a convex function? So So if I take an interval, might be a closed or open or infinite, or I don't really care, just any kind of interval. So a function, let's say phi from I to the reals, is said to be convex or convex if I take, let's say, lambda times x plus 1 minus lambda times y, it's at most lambda times phi of x plus 1 minus lambda phi of y for all x, y in the interval. I'm sure you've seen this before, right? I mean, most people. Or if you haven't, then it doesn't really matter. It's not that deep of a concept, right? The thing is, most of the functions you apply this definition to are kind of natural ones, like, for example, phi of x equals x squared, right? We graph this. So the key property is if you draw a line, if you take 2 points on the graph of the function, so like think of the 2 points as x and y, right? The like lambda phi x plus 1 minus lambda phi y. Oh, so sorry, this is for lambda between 0 and 1, right? If I take lambda phi x plus 1 minus lambda phi y, that's defining a line segment between phi of x and phi of y. If I let that run from lambda equals 0 to lambda equals 1, right? So like convex means the line segment from phi of x to phi of y lies above the graph of the function phi. That's all that means, right? Another thing to think about is if phi is twice differentiable, so convexity just means that the second derivative is not negative everywhere. Okay? So like it bends like upwards, right? Maybe thumbs up or down. Who feels like this is familiar or unfamiliar stuff? Okay, good, good. So Jensen's inequality is kind of the key thing about convex functions. I guess the thing about this course, the prereqs are like, you have to do Math 222. So, I don't know whether everyone's going to come in with this background. So I do need to kind of, it's also good to see it though, I think. So Jensen inequality says that if phi is convex, then for all, if I take point z1 up to zn, in the domain. So let's just call the domain I, like it in the definition over there. And if I take real numbers, and so positive real numbers a1 up to an, summing to 1, then we get some kind of inequality here. Okay, maybe to test your intuition with convexity, really quickly, thumbs up if you think it goes this way, and thumbs down if it goes this way. It's a 50-50 shot. Actually, if you want to know the answer, like, think about the case n equals 2. And then actually, like, just look at the definition of convexity. It's got to be thumbs up, I think, right? Because actually, in the case n equals 2, think of this, z1 is x, z2 is y. a1 is lambda, a2 is 1 minus lambda. It's got to go this way, right? So this is just a generalization of the basic definition of convexity. Like convexity says for 2 points, you can do this. You can split it in this linear way and get an upper bound. And this says for n points, you can split it linearly and get an upper bound, right? That's all it says. Is it clear what this is saying? How do you think you prove it? I like that, yeah. Like induction on what? It's a natural choice, yeah. I mean, it's pretty natural, right? Because we don't know anything about convex functions except for this, right? And this covers the case. Okay, the case n equals 1 is kind of trivial because both sides are. Wait, is it trivial? Well, yeah, because the case then a1 is 1, so it's just the same thing on both sides. The case n equals 2 is just this, right? But then, so how would you do the inductive step, do you think? So now n is n, not 1 or 2, but. Roughly speaking, not like actual, any thoughts? So let's say n is 3, right? So yeah, induction is kind of the right thing. Again, all we know about convex functions is that thing. So if n is 3, split off, take the last term and take the other 2 terms, treat those as 2 terms, and somehow apply convexity to split off the last one, and then take what's left and then split that by induction, right? So that's the whole proof, really. Does that make sense? I can do it for real if you want. But actually, I mean, okay. The point of this is not so much about how to prove Jensen's inequality or Jensen's inequality. I'm not sure which it is. But the point is really about how do you use that. So yeah, if it's okay, maybe I'll skip the proof of that. Basically, the idea is split off the last term, apply induction. Okay, so let's see a consequence of that. So holders inequality. May thumbs up or down. Who's familiar with this, at least this name, holders inequality? Like, yes, no? Okay, so I've now we're moving on to things that are new for some people at least. So, okay, let x1 up to xn, y1 up to yn be reals. And let p and q be bigger than 1, or yeah, such that this weird condition holds. 1 over p plus 1 over q is 1. So for example, if p is 2 and q is 2, that would be an example, right? Half plus a half is 1. That's kind of one of the more important examples. So then, if I sum up from I equals 1 to n of the absolute value of xi times yi, that's at most if I sum up the, so I'm really running out of room here, the pth power of the absolute value of xi raised to the 1 over p, and then sum up the qth power of yi, and then on the outside of the sum, take the qth root. Okay. Again, for all intents and purposes, it's not so important to know how to prove this, although I will prove it now. But really the important thing is knowing how to use this. And that's what we're going to see throughout the course. We're going to use this in lots of different ways. But let's prove it. Okay. So basically I want to apply Jensen's inequality, right? So I need some zi's to plug into Jensen's inequality. So I'm going to let them be xi over yi to the q minus 1. So for I from 1 to n. And I need some numbers ai, which are going to be, so ai is yi to the q. So, and then I kind of need to normalize this because at least the way I've stated Jensen's inequality, these ai's add up to 1. So I need my ai's to add up to 1. So as long as I do this, then if I add up all the ai's, it'll compute the same sum as the denominator, right? So it'll add up to 1. Okay. This is the kind of proof that, I mean, I can't possibly memorize because all of these things just seem too wacky and weird, but it works out. So here's the thing. The function x to the p is convex, right? Because, well, p is bigger than 1. Okay, it's still convex if p equals 1, but yeah. So for example, take the second derivative. It's going to be non-negative. Oh, well, convex, when I say convex, I mean on the set 0 to infinity. Right? It doesn't work if you go to the negatives. Okay. So now I'm going to apply, so maybe I'll erase everything except this inequality. So I'm going to apply Jensen's inequality to this thing, these z's and these a's. So Jensen implies that, well, if I take phi of the sum of the ai's, zi's, which means raising it to the p, so I'm using phi being the function x to the p. So that's supposed to be at most, if I sum and take ai on the outside and just apply phi to z, right? Okay, so let's plug in stuff. Well, let's first just take the pth root of both sides. So I'm just going to get rid of that, right? Pth root of both sides. So now the left-hand side I can rewrite as to the q okay. So I kind of understand this is not a very enlightening proof. But yeah, we need to know this because we need to use it for more exciting things later. This side, what do I get? So all I'm doing is plugging in the values. Okay, now to be q minus 1 times p. So this is my zi to the p is here, and this is my ai, right? Okay. Okay, so this is kind of looking, we've got some of the stuff we want, right? So we've applied Jensen. I don't need this anymore. Well, we are kind of out of time, so maybe I'll just say, if we rearrange this, and use that this q minus 1 times p is equal to q, because here I'm using this 1 over p plus 1 over q equals one thing. If you rearrange this, you can get this. So that's just a Q. Yeah, you end up getting what we wanted. Okay, so all of that algebra is fleshed out in the notes, but yeah, the key thing is to apply Jensen's inequality. Okay, so I understand that was a bit of a dry kind of thing, but yeah. Next time we're going to do something more exciting.